Hello everyone, that's me, Godfrey, changing code on the internet. This is the Portland Ember meetup. Hopefully you're at the right place. As Leigh mentioned, I will be talking about Glimmer, and then Yehuda will be talking about the future state of Ember after this. And then personally, I'm most excited about this. There's a third talk about networking after Yehuda's talk. So if you didn't read the description carefully, you probably missed it. But yeah, that's going to be my favorite talk for tonight. So Glimmer, future state of Ember, and networking. I work for a local company called Tilde. Yeah, we have a product called Skylight. It's a performance monitoring application for your Rails app. So if you use Rails in production, you probably want to know how your app is doing in the wild, and you probably want to know how you can, if any parts of your app is slow, and if so, what can you do to make it faster? And Skylight is the app to help you answer those questions. So you should sign up if you use Rails. You can sign up at skylight.io. And even if you're not using Rails, we actually have an insider email newsletter thing for our customers. So usually we talk about the work that we're doing, the features that we're building, but occasionally we also talk about random things like, oh, I ran into this problem today and here's how I solved it. Or like, I ran into this problem and I don't know how to solve it. Does anyone know? If anyone knows, please tell us. And sometimes we talk about random things like Glimmer and, I don't know, like profiling in Chrome and stuff like that. So even if you're not using Rails, you might still want to sign up. I think Rocky and Kristen just sent out one of those insider newsletters today. So you probably missed that one, but here you can sign up at skylight.io. Or if you would like to help me, this is my personal referral URL. If you need pen and paper to write it down, I'm sure Leah and Crystal can help you. So we're here to talk about Glimmer 2. But before we talk about Glimmer 2, I also need to thank LinkedIn. Tilde and LinkedIn have been sponsoring part of our time to work on Glimmer 2, and without that, it probably wouldn't happen because it takes a lot of effort for Yehuda and to work on this on our personal time, and having LinkedIn and Tilde sponsor our time to work on this is really helpful for this project. You probably heard about LinkedIn recently in the news that they have been acquired by Microsoft for $26 billion, one of the biggest acquisitions this year. You're probably wondering where that valuation came from. The answer is very simple. They have the most punnable two-letter word in the English language. For example, if you go to the office, you'll see that they have been using this pun everywhere. And I think they could probably hit a little bit harder on that. For example, in the parking lot, they could have it sign up like that. They could call their design team, the InDesign team. And on the website, they probably could have done that. And finally, I think this acquisition makes a lot of sense for Microsoft because, there you go. So if you would like to connect to my professional network, you can email me at gchan@linkedin.com. That's also where all the recruiter emails goes. So Glimmer 2. You probably heard about Glimmer 2 by now. Glimmer 2 is the next generation rendering engine that Yehuda and I have been working on for the past year or so with a lot of help from other Ember contributors. So that's Glimmer 2. But instead of talking about that, I decided I would like to talk to you a little bit about programming language implementation today. So sorry for tricking you to come here thinking you would hear about Glimmer 2. So the point of this talk is not to help you become a programming language implementer or a VM hacker in half an hour. That's a pretty tough thing to do in such a short talk. But I think the point of this talk is to help you form a mental model around some of the tooling you use every day at work. Glimmer 2 is part of that, but also you might be surprised that a lot of other things are actually related to programming language implementation techniques, even though it doesn't look like that on the surface. And hopefully I can convince you by the end of the talk that these things are less scary than you think. Like the name programming language implementation sounds pretty scary, but hopefully by the end of the talk, it would be, you realize that it might be more straightforward than you think. And finally, I hope to convince you that learning about some of these obscure or niche topics could actually help you solve real problems that you might encounter at work or on your side projects in unexpected ways. So, before we talk about that, we need to get some of the definitions out of the way. So the first thing I want to talk about is a compiler. What is a compiler? A compiler is a program that takes some input and produce some output based on the input. So now we have to be a little bit more specific than that because that basically is literally every program ever, right? It takes input and produce some output. So compiler specifically takes a very special kind of input and produce a very special kind of output. What is the input and what is the output? Well, a compiler is a program that takes an takes a program as input and transform that into different program as output. Concretely, you might think that compiler, oh, it's like the thing that turns my C code into a binary executable. But that's a pretty narrow definition of the term compiler. I specifically didn't say it takes source code and produce executable, or I said it takes an input program and transform it into a different program. Right, so actually that covers a lot more things than GCC or like the Java compiler. For example, you probably use a program called Babel in your Ember app. So if you didn't know what it is, Babel is a program that lets you write ES6 code today and transform that into ES5 code that is more commonly understood by the browser. So that allows you to use things like classes, arrow functions, and stuff in your Ember app, even though the browsers that you're targeting don't necessarily support those syntax. Right, so a lot of times you will hear people refer to Babel as a transpiler, but a transpiler is actually just a special kind of compiler. There's another name for transpiler called a source-to-source compiler. Right? So it takes an input program that is in the form of source code, and it produces a different program which also happens to be in the form of source code. So it takes some source code as input and produces some different source code as output. So that's a source-to-source compiler or a transpiler. Other kinds of compiler that you might not necessarily think of them as a compiler, but also fall into this wider definition of compiler includes things like a minifier, which takes your JavaScript files and turn it into more compressed format by removing the names, white spaces, and things like that. Or perhaps a decompiler, which takes a binary and try to produce the source code from the binary. Or things like a rewriter, or even fancy things like compiler. So the takeaway is a compiler simply takes a program and produces a different program. The program could be in various different kind of formats. It might be source code, it might be binary, it could be many different things. Okay, so now we know what a compiler is. We must ask the question, why bother? Why do we need compilers? Why do we need to compile things? The naive answer is, oh, you need to compile your program in order to run it. Right? That sounds true because you can open up your text editor, you can write some C code, and then I cannot run it. I have to compile my C code before I can into a binary executable before I can run it on my computer. So that sounds true, but it actually isn't that true. So to understand why that's not technically true, we need to dive a little bit deeper into what is inside a compiler. So conceptually, you might have seen something like this. So you can imagine a compiler is a box, and inside the box there are two other boxes. There's the front end, and there's a back end. So these are not necessarily two components in a compiler, but for the purpose of understanding a compiler, this is how we usually describe it. So these are like two logical parts of the compilers that do two more or less distinct kind of tasks. So, right, so these two parts takes on two different kind of responsibility. So in the case of the compiler that takes your C code or Java code and produce a binary executable, the front end and back end can also be called the parser and the codegen. So the parser, basically so we came from this slide, right? So if you pay attention to the two boxes, they're front end, back end, parser, codegen. So these are just different kind of names that we can give to these things. So the parser basically takes the source code. Your input program is a source code, so like that's the strings that you type on a computer that you can kind of read and write as a human. So the job of the parser is to take that source code and turn it into a data structure that is easier to work with. So the output of that step is called IR, or the intermediate representation. So the point of this step is, while it's true that the source code is very easy for you human to work with, that's like if you have to imagine writing a program to manipulate the source code, it gets pretty complicated, right? Like you have to ignore the white spaces, and you have to figure out, like are things separated by a semicolon? Like what is this line of string? Is that a string literal? Is that like there are a lot of different things encoded in the syntax to make it more pleasant for you to work with, but that's not so nice if you have to write a compiler based on manipulating the strings that you type into your text editor. So the parsing step is basically just take that source code and try to turn it into a more friendly, more computer-friendly data structure that you can work with. So we'll talk more about what that data structure looks like in a little bit. But for now, let's turn to the second part. So the second part, which we call the backend or the codegen, is basically, now that you have this data structure, now that you have a machine understandable representation of your source code, you can take that and turn that into your, and produce the binary that you run on your computer. So if you're talking about a C compiler, you will have a .c file, and you would run it through the parser, and now you have an AST or syntax, you have an IR of the C source code that you typed, and now you run it through the codegen, which generates the binary that you can run on your computer. So that's the compiler. So now that we roughly understand, like the details are not very important here, but the key is compiler logically, there are two parts. There's a front end, there's a back end, or you can call the parser and the codegen. So the parser takes care of parsing the program, trying to make sense of the program, turn it into data structure that's easy to work with. The codegen actually takes care of compiling the source code into the machine code or whatever. And so now that we understood roughly what the compiler is doing, we can go back to the question of why do we need this? Why do we need a compiler? Well, actually, the answer is we don't technically need the compiler because instead of, so we said, oh, the reason that we think we need a compiler is we cannot, like, the computer doesn't understand your source code. The computer doesn't understand your C code, right? So in order to run it, you have to run it through the compiler, get the binary, and now you can execute the binary. But actually, there is another kind of program called an interpreter. So instead of, so that you can see that this slide looks pretty similar to the previous slide, and the only difference is on the right-hand side. So actually, instead of running through your program through a compiler, you can always instead run it through an interpreter. So what an interpreter do is still run it through the parser, right? So you get your source code, you run it through your parser, and now you have an intermediate representation that it's easy to work with. So instead of taking that intermediate representation and generate machine code for it, you can actually just run the machine code that you're about to generate instead of putting it into a binary file and then run the binary. Right, so, so that's basically the idea of an interpreter. So basically parse into IR, and then you just loop through the IR and then do whatever you're supposed to do with the whatever the programmer is telling you to do. You're probably familiar with this in the context of scripting languages like JavaScript or Ruby or Python, things like that. Right? So for example, when you type node in your command line, the thing that pops up is an interpreter, right? Like you can write source code in there, and then it would run them for you. Or when you go to Chrome and open the developer console, you get an interpreter. But you can actually do this for any kind of languages. Like, so then the way to intuit it is, oh, like if you can, like if you can look at the IR and then generate some bytes in the binary and run those bytes later, you can obviously just put those bytes into memory somewhere and then just tell the computer to please run this immediately. So you can actually, instead of compiling a C program, you can always just interpret a C program. So given that it is always possible to interpret instead of compile, why do we need compilers? What is the point of compiling? It's actually pretty nice to be able to bring up the node prompt or the Chrome console and just type stuff into there and like have it run immediately. So if that's possible, what is the point of compiling your C code or Java code into a binary before running them? So the answer to that, or at least from my perspective for today, for the purpose of this talk, I would argue that the point of compiling is usually to front load some of the work to compile time to reduce the runtime costs. So basically, there are a lot of work involved in running a program, and by having a compiler, you can do some of those work when you compile the program, so you can try to get a deeper understanding of the program and try to do some smart things and put that result into the binary. So every time from now on, now that you have an optimized binary, every time you run it, you pay the runtime performance is a little bit better because you did some of the work ahead of time and encoded that into the result instead of having to do that every time. And so on top of that, there's also another reason. So like I said, if you have a compiler, usually what you're doing is you're compiling this program ahead of time, right? So for example, you are running the compiler on your build server before you ship it to your customer. So it actually doesn't matter if the compile phase takes a little bit longer. You can afford to front load some of the work, or you can afford to do a little bit more expensive things when you compile stuff. And so your customers don't have to pay that cost when they run your program. So your customers can get a more optimized version of your program instead of having to pay the same cost every single time at runtime. So one way to do it is you can have an explicit optimization path, which basically takes Like, so you run your source code through the parser, and now you have a data structure that's easy to work with. And now you can put it into another program called the optimizer, and you can look at it. Oh, I see that these functions are never called, so let me remove it from the data structure. Or I can see, this function is actually really small, so let me inline that into all the places that it's called to avoid paying the cost of the function call every time you need to execute that function. So we won't get into too much of the details here, but you can intuit that, like if we can afford to spend a little bit more time when we compile the program, we could do some smart things here and try to make the output more optimized. So that is all we're going to talk about for compilers and interpreters. So what does that have to do with template rendering or Ember? Well, so here's a handlebars template. If you have not used it, it will probably look familiar to you because that's just HTML. However, if it's just HTML, it's pretty boring. So here is another example of a handlebars template that you might write in your Ember app. So here we have a variable, dynamic variable there. So what would happen is every time you run this template, you would substitute that curly name with perhaps the name of the user, something like that. And in addition to variables, you can also have helpers in handlebars. So for example, you can have a format currency helper that takes the price and then turn it into a human readable format. Or you can have a URL for a helper that takes a route name and convert that into a URL. And you can, on top of that, you can also have components in Ember. So for example, you're using Font Awesome, the icon library, and you are pretty tired of typing all the incantation to get the icon. You can abstract that into a component like FA icon, and you can pass some arguments to it, and it can put the right icon on the screen. Or you can do more fancy things, like you have a fancy button, and you can have a callback for what happens when you click the button, and things like that. And finally, there are also some limited control flow structures in handlebars templates. So for example, on the top, you have an if statement, so you can toggle between two different templates based on whether some condition is true. Or you can add and remove a class based on some other condition. Or at the bottom, you can have each loop that loops through a list of users and do something for each of the things in your array. So if those look like programs to you, then it actually is true, right? Handlebars templates are programs. Templates are programs because they are doing a lot. They are in fact doing a lot of things that you would find in normal programming languages. So if templates are basically restricted a mini programming language, perhaps an idea to make them faster is we can look at how programming language implementers implement programming language, how they optimize programming languages, and draw some ideas from there to see what we can take to apply to our handlebars template rendering problem to make it fast. So handlebars always had the concept of a compiler since the very beginning. And according to Yehuda, who made handlebars, he said that was one of the main reasons for forking Mustache and making handlebars. So, remember a compiler, if you remember from the beginning of the talk, a compiler is just a program that takes a program and transforms it into a different format. Right? And the point of compiling is to move some of the runtime costs up front, so it becomes a little bit cheaper to run. So in particular, while the handlebars templates are very, very human readable, it takes a non-trivial amount of work to parse the handlebars curlies into something that you can render on the screen, right? So for example, if you are just given this string as this line as a string, and you have to render that on the screen, you would first have to understand, oh, I need to maybe separate out the curlies, and then I see there's a pound at the beginning, so that's a block, and do a lot of different things to even understand what this line is talking about. So that's basically the point of the handlebars compiler. So while the templates are very human readable, and that's great because you want to optimize for human productivity when you're editing them, it's actually pretty difficult for the machine to understand them. So the point of the handlebars compiler is to do the parsing step on the when you build your Ember app, so that you don't have to do that on the browser every single time, right? So you can intuit that if we have to do the work to take this string apart and separate that into the meaningful pieces on the browser, it gets pretty expensive. So the solution is to have the handlebars compiler do the compilation when you run Ember build, right? So when you run Ember build, it actually look at your templates, try to run it through the parser, and then do some compilation, and then emit a JavaScript program for each of them. So whenever your user need to whenever your user go to your Ember app, what they're getting back is just a JavaScript program, and Ember can easily work with that. And so another point is that Ember, modern Ember actually does more than just using the stock handlebars compiler. We have a HTML parser, an HTML spec compliant HTML parser called HTML bars. So that's a project that we started probably 2 years ago or something like that. So instead of only parsing the curlies, we now also do some smart things with the HTML embedded in the templates, because as it turns out, most of our handlebars templates in an Ember app is HTML. So if we can understand that in the compiler, we can do more things with them. So that is handlebars. So remember, the current state of things is we take when we built the Ember app, we take the handlebars templates, we run it through a compiler, and now we have a JavaScript program, and we can just essentially you get a JavaScript function back instead of the strings. So you can just call the function, hey, here is the data, please render yourself. So there's one problem though, actually there are multiple problems, but we will focus on one of them today. So the handlebars language is actually very simple. So that's nice in one way, in one sense, but it's also problematic in other ways. So for example, when I said the handlebars language is very simple, I guess I mean the language is very small, and all you have to work with is curlies, curlies, and curlies. For example, here in hello name, it might look like one thing to you, but actually you can't really tell whether curly name is referring to a local variable, or if that's referring to a property on your controller or your component, or it could even be a helper, right? Like you could happen to have a helper registered in your app called name, and this actually resolves to a helper. Or perhaps it could even be a component. Usually that's not true, but for example, and if you use Ember, you know that there's a component called input, right? Like so, usually you need to have a dash in your component name, so we kind of know this is probably not a component, but there are certain exceptions, like the input helper or the input component. So therefore, in practice, even though we actually understand the structure of this template in our handlebars compiler, there are only very limited things we can do to it, because this is totally dynamic. It depends on what you have in your app, so I guess we have to defer to the app to resolve this later anyway. So that's unfortunate, because we actually would like to do as much as possible when we compile your templates, instead of having to ask the question of what is this name referring to every single time we render this. So therefore, in practice, even though everything is pre-parsed and the DOM building code is compiled into JavaScript on the server, into JavaScript function on the server side, and when you run Ember build, all of the interesting work that needs to happen to resolve things like this actually happens at runtime anyway. So every time this line is executed, you have to ask all of those questions again. So this is a very specific problem, but it perhaps gives you a good intuition of what is the kind of things that you would like to avoid but you can't currently do. So that might not look very expensive, but for example, if you have this wrapped up in each loop and you have a very big list, those costs could start to add up. So like I said, this is not the only problem, and this is perhaps not even the most fatal problem, but it gives you a good intuition of the kind of problems that we want to solve here. And the fallout of this problem and all the related problems that I couldn't cover here is that rendering components are pretty slow in Ember today. It's not slow enough to be a problem for most apps, but Ember is all about building ambitious apps, right? And on ambitious apps, like for example, LinkedIn is building their mobile web app on Ember, and they have a lot of stuff going on in the app, right? So when you do this a lot, and if you use a lot of components in a really big app with a lot of data, this could add up quite quickly. This is pretty unfortunate because everyone loves components in Ember, and it's among other things, it's a great refactoring tool, right? Like if your templates get too big, you want to move that out into subcomponents, and if you couldn't do that, that's like if you have to pick between good, easy to maintain and easily readable code and performance, that's a pretty unfortunate trade-off that you have to make. So given, okay. So like I said, if it turns out that templates are just, handlebars templates are just a mini program, we should try to borrow some ideas from people who implement program languages and you see what we can do to make it fast. So one of the ideas we stole from programming language implementation people is called adaptive optimization or runtime optimizations. The idea is that in general, there are a lot more information you can use to optimize a program at runtime versus ahead of time at compile time. Because the runtime your program is actually running, and you can answer a lot more questions about what. So perhaps I should put it in differently. So when you're compiling a program, all you can do is you can understand the structure of the program. But when you're actually running the program, you can actually see inside what the program is actually doing, and there is you can collect a lot more information to help you optimize the program accordingly. So in our example here, it is true that when we build the templates, we don't actually know what this name referred to. But actually, when we run this for the first time, we actually know that name could either be a local variable or a property on your component, or it could be a helper. And once we know the answer to that, it isn't going to suddenly change from that point onwards, right? So the first time, as soon as we find out, oh, this is actually a helper, or as soon as we find out this is actually a local variable, that is not going to magically change on us on subsequent invocations. So therefore, it actually seems, if you think about it, it seems pretty silly that we have to ask that same question every time we invoke this or on every iteration of the loop. So the solution to that is we added another compiler. So remember, if you remember, the job of a compiler is to do some of the, or the benefits of a compiler is that you can take some of the work you have to do anyway and move that up front and reduce the cost of subsequent execution. Right? So that's exactly what we want here, and that's exactly what we did. So instead of sending down the compiled JavaScript functions from the build time compiler, what we did in Glimmer 2 instead is we actually just serialized the intermediate representation down to in a JSON format, and we actually do another pass to compile the program in your browser before we actually execute it for the first time. So this kind of compiler is often called a just-in-time compiler or a JIT compiler, just because it lazily compiles the stuff that you're, it lazily compiles your code just before they're executed. So this compiler, because this compiler lives inside the browser, lives inside your Ember app, it allows us to use the runtime information for the triage work. So in this example, because it happens in the browser, we can actually ask the resolver in your app, oh, is this a helper? Okay, it's not a helper, then it's a local variable, that's the end of the story. And we know for sure at that point that it's not going to change. So, right. So now, then, we have, we know that we have a compiler, but what does that compile into? So we could, remember the current, before Glimmer 2, what we did on the build time compiler is we basically compiled that into a JavaScript function that we can invoke with the data. So we can do the same thing here. We can actually, in your browser, even though we're in your browser, we can still take the IRR, do the optimization, and then compile it into a JavaScript function. But there are several problems, and among other things, it actually gets pretty complicated, and in the end, it doesn't make things that much faster. And instead, there's a more direct way to do it. What we do is we take a program and we compile them into a list of instructions for our VM written JavaScript. So that all sounds very fancy, but actually that is just a rebranded version of the concepts that we already know about. The VM instructions here are sometimes just called the IR in some other context. So IR, again, is the intermediate representation. So the only reason I didn't reuse the word is because we already have another IR on there, and it would be pretty confusing if it's multiple IRs on the screen. So another name for that is bytecodes, and you probably heard about that in other contexts, like when people talk about Java, they talk about taking Java code and compile it into Java bytecode, right? So that's actually interchangeable with, and the IR is also interchangeable with VM instructions. And if you remember the interpreter that we talked about early on in the presentation, well, actually, a VM or a virtual machine is just, or at least in this context, another name for a VM is an interpreter, specifically a bytecode interpreter. So you can basically, for example, Java, the JVM, you can interchangeably use, like you can call that the bytecode interpreter, for example. So the point of the VM or the bytecode interpreter is basically, oh, now we have a list of instructions, or now we have an IR that we can work with. Let's just loop through it and like do whatever we're supposed to do with it. So more concretely, this is what actually happens. So here you might have a, like hello world, you can't actually tell what it is, but I can tell you, in this case, it is a component. Right, so then here's your component template or component layout, and this is what you would, if you actually ran that in your, if you actually have that component in your Ember app, the output in the DOM would look something like this. And so how do we actually get there? Well, we, in Glimmer 2, what we do is we take the first, like we take your template, in the build time compiler, we turn that into an an R that we can serialize in JSON format, and then at compile time, at runtime, we take that and we turn it into a list of instructions that we can use to render the component on the screen. So that looks pretty scary, but if you actually look at it, it's actually not so bad, right? So basically, each line is an instruction that we execute, and each line is focused on doing a very specific thing that eventually lead to this being rendered on the screen. So for example, if you look at number 4, basically, if you look at line number 1 and line number 4, that's basically it's doing putting the diff component on the screen. So we don't have to go into too much of details here, but one of the benefits of this approach is that it's very easy to visually see what kind of work is involved in rendering a very simple component on the screen like that. And it makes it easier to measure the cost because we have a very concrete list of tasks that we're looping through, and we can measure how long it took to execute each of the mini tasks or each of the instructions we have. And it's also make things more easy to optimize. And if you concretely look at it, you realize, oh, actually, a lot of these things are about features that we are not using in this component. So for example, it turns out in Ember, you can customize the tag name of a component even, so you can customize the tag name of a component by reopening the class and put a tag name in the component class, but you can also do that when you invoke the component in the template, right? So you can do curly, hello world tag name equals li, and that completely changes everything. And more, in addition to that, you can also use a tag name equal empty string, and that becomes a tagless component, which does a completely different set of things. Likewise, there's a feature called aria role in Ember components. So for every component, if you have a property called aria role, it would add the role property on in the HTML, and there are a lot of dynamic things like that, and all of those are customizable from the template invocation, from the invocation side. And that kind of sucks because we're not using any of those features in this particular component, right? So one of the benefits of having this runtime compiler is that we can actually look at a component and say, oh, okay, we are actually not using those features. So we can just optimize the component by removing those instructions from for this particular component, right? So we can do smarter things at runtime for each individual component because we have a lot more knowledge about how that component is being used in practice. So that the goal is eventually make a lot of those legacy features that we have more pay-as-you-go. So if you're not using them, then we don't have to make you pay the cost for them, and that in turn help with our mission of maintaining stability with automation, because now we can, at runtime, detect a lot of the features that you're not using and just save you from paying the cost for that. So that's the Glimmer compiler, and I guess I'll skip over this part, but actually, I can also skip this part because Yehuda is going to talk about it next. So the main question you're probably wondering is, oh, okay, so that all seems pretty cool. When is that happening? When I first wrote this talk, I had on the slide soon, but actually, it already happened. So a few weeks ago, we shipped a beta 2.9 beta that includes the first version of the Glimmer 2 integration, and you can read more about the details in the blog post. But we tried really hard to make it a drop-in replacement for existing apps, so you should, in theory, be able to just bump the version and get the benefits without having to do any work. So if you have some time this weekend, you might want to try your app on 2.9 beta. One of the cool things that is relevant to what we just talked about is, if you remember I mentioned, currently we're compiling the templates into JavaScript functions and sending them down the wire, we switched to sending a JSON representation. And one of the nice fallout from that is their template size are a lot smaller. So intercom, so Gavin tweeted the other day that intercom, it's a pretty big Ember app. If you didn't know, they use Ember. Before the Glimmer 2 upgrade, they have like 1.3 megabyte gzip in their app bundle. Like, so most of that comes from templates, and after upgrading to Glimmer, their gzip size went down for another 30% or so. So that's one of the pretty cool fallout from the project. And this is a very narrow slice of the entire project, right? The entire project is actually much broader than that, but this is a focused piece of the work that we have time to discuss today. So that's my talk for today.